Okay, günaydın. Uh, Welcome again. So let me start by reminding you what we were doing last week. We showed that the space of bounded functions with supreme metric is a complete metric space, and then we uh, also showed that the subspace of continuous functions on a closed interval uh, is also a complete metric space. It's a closed subset of bounded functions on the closed interval. And then we start to discuss continuity of functions for defined on metric spaces. This is the definition for a continuous function, for a function to be continuous on real line. And we may formalize continuity as follows, right? Okay, I went too much. In terms of balls, so a function is continuous if for any epsilon positive there is some delta, so that the delta ball is mapped to the epsilon ball, right? The delta ball around x0 is mapped to the epsilon ball around f of x0. And we use this definition for functions defined on real numbers for functions on a metric space, because once we have balls, then we are ready to state it in the setting of metric spaces, uh, and this is the definition, the same definition, uh, and this was where we had stopped last time. Now let me continue from this. Okay. Okay, we have a slightly more strong definition of continuity, so-called uniform continuity. Let me also talk about this, or maybe I can talk about it later. Let me first give you a definition of continuity in terms of sequences proposition. A function f from a metric space x to another metric space y, so these are metric spaces, is continuous as above at some point x if and only if for every sequence xn with limit xn equals x, we have limit f of xn equals f of x. So you also recall this definition, right? This is the definition we used for also functions defined on real line. So the definition defined given using epsilon delta is equivalent to this definition for sequences. Okay, here is the proof. First, let's assume that so let's prove this direction. Assume that f is continuous at some x in x. And let xn be a sequence with limit xn equals x. So what I need to prove, I must prove the following. We must prove limit of f of xn equals f of x. Right? This is what I need to prove. How can we show whether a sequence is converging to a point or not? Well, we have to use the epsilon delta definition. Epsilon definition for sequence. Okay, so given epsilon positive, well, since my function is continuous by assumption, right? We assume that it is continuous. It satisfies this hypothesis. So, since f is continuous at x, there is some delta positive, so that uh, the distance between x uh, and y is less than delta, implies the distance between let's say f of x and f of y is less than epsilon. Okay, well, I know that, so I have this. Let me draw you a picture. Okay, here is, let's say, x in the metric space x. Here is the point y, and you give me some epsilon ball. Okay, epsilon ball. Maybe I use a different color. Okay. Okay, let me. Okay, so this is the epsilon ball, and this is my. Okay. F of x, and I have a delta ball around x, so that its image is mapped to this epsilon ball. So that's the picture. But I have the following. My sequence xn is converging to x, right? So x1 might be somewhere here, x2, x3, and so on. But I know that since the limit is x, after some index, the sequence falls into this ball. Therefore, its image will fall in the epsilon ball. Right? This is the picture in the xt metric space. This is in the picture in the y row metric space. So let me write that down. Since limit of xn is equal to x, and the radius here is delta is positive, there is some n0, so that n larger than n0 implies the distance between x and 0 is less than delta. But if this distance less than delta, then this distance is less than epsilon. In particular, uh, the row distance between f of x and f of x n, not n0, f of x n is less than epsilon, right? Provided that n larger than n0. So what we have done? We have done the following. Given epsilon positive, I found some n0 so that n larger than n0 implies this distance is less than epsilon. This implies what? Hence, limit of f of xn is equal to f of x0, f of x in the metric space y rho. So this finishes the if direction. For the only if direction, we will proceed as follows. Okay. Now assume that, so I will show what we assume now that f is not continuous at x. So I am assuming the opposite, the negation of the statement that f is continuous, and I must show what. So my statement is what? F is continuous if and only if for every sequence converging to x, I must have this. Now I assume that f is not continuous, so we have to find what? I have to find just one sequence so that that sequence is converging, that sequence will converge to x, but its image won't converge to f of x, right? This is what I need to do. Uh, Hence, we must construct or find a sequence xn in xd so that the limit of this sequence will be x, but f of xn will not, so limit of, okay, limit of f of xn will not be f of x. And how can you show that this sequence is not converging to this? Well, you have to find an epsilon so that there is no n0 with the following property. There will be always some integer larger than n0 so that the distance between f of xn and f of x will be at least epsilon. Okay, so this is how I will proceed. Since we assume that f is not continuous, since we are given that f is not continuous, at x there is some epsilon positive so that for any delta positive there is some y in x with dxy is less than delta, but rho of f of x and f of y is greater than delta. Sorry, epsilon. Okay. Now, this is what I will use. Now, choose now uh, for any uh, n0 for any n, choose okay, xn with right, for any delta there is some y which satisfies this and satisfies this. So for any n, I choose xn with this property. Distance between xn and y is less than 1 over n, right? This is my delta with rho of f of x and f of x, so f of x and f of xn. I must be careful. This is xn, 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 right? So my xn plays the role of y, right? This will be less than, this will be at least epsilon. So I have a sequence of elements xn in x, so that this distance is less than 1 over n for all n, and this distance is greater than epsilon. This means what? Hence, right, since this is less than n, limit of xn is equal to x. But this distance is never less than epsilon, right? I found an epsilon, and this distance is never less than epsilon. So, and limit of xn is not equal to f of x. I don't even know whether this limit exists or not, but it is certainly not equal to f of x, because if it were, after some index, this distance would be less than epsilon, but it is never. Okay, so we found a sequence in x which converges to x. However, their images do not converge to f of x, and this is what I wanted to show, right? If f is not continuous, I can find a sequence satisfying these two what conditions. This finishes the proof. Do you have any questions so far? Okay. Uh, so this is the uh, formulation of continuity in terms of sequences. Let me write as a remark. Uh, this is called the formulation of continuity in terms of sequences. We had epsilon delta definition. Now we have the sequence definition. We will see actually more equivalent formulations. Let me see. Okay, so here is another one. A function f from x to y is continuous on x if and only if. So continuous on x means it is continuous at all points. Okay, here in the above definition so far we considered only continuity at a point, right? But now we start with a function which is continuous on x, and in this case so this is equivalent to the following: if and only if for every open set subset, let's say O of y, the inverse image f inverse of O is open in X. So continuity on a space or continuity of a function defined between metric spaces is equivalent to the following: you take an open set in Y and look at its inverse image, and that should be open. Okay, if this is the case for all open subsets of Y, then F becomes continuous. Remember, F inverse of O is what? This is the set of all x's in X such that f of x lies in that subset, right? Okay, let's start from this direction. So I assume f is continuous. Assume that f is continuous at all points. So continuous on x means it is continuous at all points. And what I have to do, I have to take an open set, take any open set, open subset, O of y. We must show what? We must show f inverse of O is an open subset. All right. How can we do this? Well, how can you show a set is open? Well, the definition is that you will take a point in that set and you need to find an open ball around that point so that that open ball lies inside that subset. So take any x in f inverse of O. All right. Well, what is the definition of inverse? It is this: f of x should be in O, then f of x is an element of this set which is open by assumption, which is open. Well, open means what? I can draw a ball around this, right? Hence, thus, there is some ball. Let's say, let's take the radius to be epsilon, epsilon ball, so that the ball uh, with center f of x and radius epsilon lies inside this in the metric space y rho. So here I am using the rho metric. Okay. But our function is open, sorry, continuous. We assume that f is continuous. Now, remember the definition of continuity, right? Continuity means this. Whenever I have an epsilon ball, I can find a delta ball so that this ball is mapped into this epsilon ball, right? This is the picture. So I will apply this. Okay. Since f is continuous, uh, at all points, in particular at x, there is some delta ball. There is some delta so that f of the uh, delta ball around x is mapped into rho ball, sorry, epsilon ball in the uh, metric space y rho. Okay, so here is my f of x and my epsilon ball. Here is my x and my delta ball. Let me use a different color here, maybe. Okay, so that its image, okay, lies inside. So this is the ball in the metric space xt, and this is the ball. All right, f. So this is b x epsilon. All right. Now, uh, the image of this ball lies inside uh, this big ball, but we know that this ball lies inside uh, the open set, right? Right? It lies in this open set. Well, so you see, the image of this ball lies completely inside this open set, right? This open set is something like this. It is something bigger, right? Like this. So this is the open set O. Therefore, this ball lies inside in the inverse image. In particular, uh, this ball lies inside F inverse of O. And what happened then? You see, uh, given any given any point. Okay, so I want to show what? This is an open set. I started with an point in that set. I found some delta so that the delta ball lies inside this open set, right? Therefore, hence F inverse of O is an open subset. Okay, so this finishes the half of the proof. Now let's see the other direction. For the other direction, okay, uh, we proceed as follows. Uh, okay, take any uh, x in x and epsilon positive. So I have to find what? I have to find the delta so that the delta ball around x is mapped to the epsilon ball around f of x, right? This is what I need to prove, right? I have to prove this. I need to find the delta so that this delta ball is mapped to this epsilon ball. Okay, how can we do this? Well, uh, the ball in the metric space y rho with center f of x and radius epsilon is an open subset of y. And uh, since I am proving this direction, we assume what? We assume that inverse image of every open subset is open. Uh, so by the assumption, let's say the subset U, which is F inverse of is open in XT, right? This is my assumption. Clearly, uh, since f of x uh, okay, is in this ball because it is the center of this ball, right? X is in the inverse image, right? Clearly, f of x is here, therefore this x is in the inverse image. But I know that this is an open set, right? By the assumption, and I have a point in the open set. So finally, since U is open, there is some delta positive, right? Some radius so that the delta ball lies in U, right? Whenever I take a point in an open set, I can find some radius so that uh, the ball with that radius around x lies in that open set. But f of x lies here, uh, hence f of this ball lies in f of u, but u is the inverse image of this set, right? Inverse image of this set. So when you take its image, image of this will be contained in this set. Right? Uh, image of u, image of this is contained here. They don't have to be equal, right? They don't have to be equal, but it certainly lies in this set. So let's see what we have done. I took any point. All right, let me do it this way. I started with any point. I found some delta so that okay, I took any point. I want to show that f is continuous, right? And given any epsilon, right? I said take any delta. We found some delta so that the delta ball is contained in the epsilon ball. Thus, f is continuous at x. But x was an arbitrary, right? Since we're arbitrary, this finishes the proof. Do you have any questions so far? I guess this is kind of different what you have seen about continuity in calculus or advanced calculus courses, right? You had seen probably epsilon delta definition, sequential characterization of continuity, but I'm not sure whether you have seen this formulation, right, in terms of open sets. Okay. Well, once you have this for open sets, you have the same statement for closed sets. Let me write as a proposition. This immediately uh, gives the following corollary result consequence. So proposition. Let f from x to y be a function between metric spaces. And the following statements are equivalent. First one is the following: f is continuous on x. Second, for any open set, uh, the inverse image f inverse of O is open in X, and we also seen the following: for any x in X and sequence xn in X with limit xn equals x, we have limit f of xn equals f of x. We have proved actually the equivalence of these three conditions. The last one is this about closed sets. For any closed subset A of Y, the inverse image F inverse of A is closed in X. So this is the actually the only one we haven't seen so far. Proof. We have already proved. We have already proved that the first three statements are equivalent. So we just need to show that the fourth one is equal to the first three statements. To finish the proof, we will prove that. We will show that 3 is equivalent to 4. Okay, how can we show that? Okay, let's see. 3 implies 4. So, I am assuming here that the inverse image of any open set is open, and I must show that the inverse image of any closed set is closed. Okay, so let me start with a closed set. Let A be a closed subset, be any closed subset. I must show that the inverse image of A is closed. But you see, F inverse of okay, let's see, x minus A, yes, x minus F inverse of A, I can write it this way. This is x is just the inverse image of Y, right? Because every point of x is mapped to Y, and this is F inverse of A. But what is this? This is just F inverse of Y minus A, right? These kind of equalities doesn't hold in case when you take image, but they hold when you take inverse image. And we know what? A is a closed subset. Therefore, y minus a is an open subset, where y minus a is an open subset of y. But by assumption, now by assumption, f inverse of y minus a is open. So this is open, hence f inverse a is closed. And actually, this equality works not just for any closed or open set. This works for any subset. Therefore, if I start with an subset so that this is closed, well, this set will be closed. Therefore, uh, the inverse image of this will be closed. So, I mean, the other way around, it will be also clear. So let me actually. So this proved what? If I start with a closed set, the inverse image is closed. Now I have to prove this. This time I assume that inverse image of every closed set is closed, and I must show that inverse image of every open set is open. The proof will be the same, but I will leave it as an exercise. So this is left as an exercise. Okay. All right. Do you have any questions so far? Okay, let me stop the record.